if we do a titration where we have, you know, usual sort of setup, so suppose we have 25 cm cubed of 0.1 mole per dm cubed HCl in the flask, and then out of the burette we deliver 0.1 mole per dm cubed sodium hydroxide. Okay, so it's basically as simple as it's going to, you know, as it can be, and obviously the reaction is just a simple one-to-one reaction like this. Then one thing we could do is to monitor what happens to the pH as we gradually add the sodium hydroxide to the solution, and obviously the pH is going to increase as we start to neutralise the acid, and eventually will become neutral, and if we keep on adding sodium hydroxide it will become alkaline. What's interesting though is that the shape of the graph we get is quite dramatic. It's not anything remotely like a straight line or anything like that. What you get is something like this. So if you put pH on this axis, and this is the volume of sodium hydroxide added, then what you find is that you get a graph that looks something like this. Okay, so it's a really characteristic shape like that, and the reason it's got that weird shape is basically because this is a logarithmic function. So what it means is that if you remember the way pH works, you know, 1 mole per dm cubed acid would be pH 0, 0.1 mole per dm cubed would be pH 1, 0.01 mole per dm cubed would be pH 2, and so on. So if you think about how much alkali you need to bridge the gap, to go from 0.1 to 1 mole per dm cubed, you'd need 0.9 mole per dm cubed change, but from 0.01 to 0.1 it's only a 0.09 mole per dm cubed change. In other words, you need 10 times as much acid to make that change as that one, and then from 2 to 3 will be 10 times fewer as well. And that's why you get this characteristic shape. So around the neutral point, going from pH 6 to pH 7, it's a tiny amount of acid needed to make a big jump in pH, and that's why the curve goes almost vertical at that point, and then becomes alkaline again as the solution tends towards just being sodium hydroxide, just diluted slightly by the salt that you've formed. So you don't need to be able to calculate the details of this shape or anything like that, but you do need to be able to sketch a graph like this, and you do need to be able to put certain fixed points on it. So obviously in this setup we could calculate the starting pH. Okay, and so when you have to sketch curves like this, sometimes you have to accurately get the starting pH. So the first question you obviously ask is that a strong acid or a weak acid? If it's a strong acid, it's very easy. The H+ concentration is the same as the overall concentration if it's a strong acid, which indeed it is for HCl. So we just say, right, pH is minus log of 0.1 because it's a strong acid, and that is 1. So we know that in this case we're going to start at pH 1. If we had a weak acid in there, then we would need to know the Ka value, as you know, in order to calculate the pH, but if they give you that, then you could calculate it. So that's the first thing. If you're sketching one of these things, make sure it starts in the right place if you've got the numbers available. At the end, the pH is going to approach the pH of the sodium hydroxide that you're adding, because once you've gone past the neutral point, there's no more acid there, and so all you're doing is gradually increasing the concentration of sodium hydroxide in the solution, and eventually, if you've added enough of it, it will be dominated by the 0.1 mole per dm cubed, but it will never quite reach that concentration because it's always going to have been diluted a bit by what was happening in the first bit. So what that means is if we work out the pH of that, okay, so we can do that, remember, using Kw. So H plus is equal to Kw divided by the OH minus concentration. Okay, so it's a standard way of calculating pH of an alkaline solution, which is 1 times 10 to the minus 14 divided by 0.1, which is 1.00 times 10 to the minus 13 moles per dm cubed. And pH is minus log of that, which is 13.0. Sorry, minus 13 there. So the pH will be 13.0. So what we're saying is that when we reach this part of the curve where it's starting to level off, it will be approaching 13.0, but it mustn't go above 13 because it can't. You can't get a pH higher than the pH of the solution you're adding. So if we mark 13 on here as being, say, at this point, then what that would mean is that this curve is approaching it but not crossing it. Okay, so that's the second fixed point. Now the third thing is that we can work out what volume it would be where we get this near vertical region. When you draw it as vertical. In reality, of course, it can't be quite vertical because there's always going to be some volume change necessary in order to change the pH a little bit. But on this kind of scale, it's so close to vertical that when you sketch it, you would just draw it as a vertical region like that. And of course, we can work out that's when it's neutral. So we can work out what this volume is, and in this case, obviously, it's very easy because we've got the same concentrations. 0.1 mole per dm cubed of this and of that, then we're going to need equal volumes. So this would be 25 cm cubed. If they weren't equal concentrations, you'd have to work out using a normal mole calculation what volume of sodium hydroxide you'd need to neutralize it, and then you would draw the vertical at that point. So it's 25.0 in this case, but more generally it's the volume needed to neutralize. Okay, so if you're sketching one of these curves, make sure it starts in the right place, make sure it finishes at the right limiting pH, and make sure you get the vertical region at the right volume. So that's the simplest kind of titration curve, where you have a strong base like sodium hydroxide and a strong acid like hydrochloric acid. If you have a weak acid, it's going to be a bit different. So let's look at the case of, say, ethanoic acid. So if we change this now to ethanoic acid, and think about how that's going to alter the curve that we get. So weak acid, remember, means that it's only partially ionized in aqueous solution. And what that means is that the starting pH is going to be higher because there'll be a lower H plus concentration. And we can work out that starting pH, of course, using this relationship, which you need to know that the H plus concentration for a weak acid on its own in solution is equal to Ka, the acid dissociation constant of the acid, times the concentration. So you need to know that relationship and understand how it's derived from the definition of Ka, with a little bit of approximation that's needed in that particular case. So if you were given the value of Ka, you could plug the number in and calculate that. If you're not given the value, you just have to think, right, it's a weak acid, so the pH will be bigger than 1, and just guess, that it'll be somewhere around 2 or 2 to 3 or whatever, you know. If they don't give you the number, they can't expect you to get it right, but make sure it's bigger than 1. So we won't bother doing the calculation here, we'll just start it somewhere sort of up here to make the point. So this is where our ethanoic acid is going to start. Now the reaction is going to be the same 1-to-1 type reaction. Ethanoic acid plus sodium hydroxide goes to sodium ethanoate plus water, so it's the same reaction, and that means that if we've got the same concentrations, it will still be at 25 cm cubed where we reach the neutral point. Okay, so that the fact that it's a weak or a strong acid makes no difference to that. So we're still going to get the vertical region where it goes neutral at the same volume. And the limiting pH will also still be the same volume, because once it's neutralised, what kind of acid it was originally is neither here nor there. All you're doing then is just gradually increasing the concentration of sodium hydroxide up towards that limit. So it'll still end up somewhere close to 13. The key thing that's different though is if you actually do the experiment and you measure the curve, you get something that looks a bit like this. Okay, so the top half of the curve closely mirrors what you get from the strong acid, but the bottom bit is completely different. And that's because if you think about it, in this region you've got a weak acid on its own to start with, and at this point you've reacted all of the acid, so you've just turned it all into the salt at that point. But in between you have a mixture of the weak acid you haven't reacted yet and the salt that you formed. And of course, if you've got a mixture of a weak acid and a salt, you have a buffer solution. So this rather flat curve here in the middle is where it's buffering, and that's very characteristic of a weak acid titrating. So they're not too worried about the shape of this, because that's kind of a complicated issue. What they're going to look for when you sketch these curves is where it becomes vertical. And you can see that for the strong acid case, pH 7 comes kind of in the middle of the vertical region. So in the purple curve, which was the one with hydrochloric acid, pH 7 comes kind of in the middle somewhere of that vertical region. But with the weak acid, it only really starts to become vertical around pH 7 and then beyond it. So that's the really distinctive thing, that if you have a weak acid titrated with a strong alkali, you get a vertical region, but only above pH 7. Because the buffering effect has then gone away, and you just, exactly as we were with the strong acid, you're really just gradually decreasing the dilution of the sodium hydroxide, or increasing its concentration. But here is where you have the buffering effect. So that means that you can distinguish what kind of acid you're titrating, weak or strong, just from the shape of this curve. If you have a vertical region that extends well to either side of pH 7, you know, somewhere between, you know, maybe, you know, 3.5 and 10.5, or something like that, that's what you expect for a strong acid. If it's a weak acid, it will only be vertical outside the acid region where it's buffering, so it'll only be vertical above pH 7 if you have a weak acid. So these curves are very useful because you can tell whether an acid is strong or weak just from the shape of the curve, and that's something you're very likely to be asked to do. So now let's switch things around a bit and go back to having a strong acid, but look at what happens if we have a weak base. Okay, so we've done weak base and strong, we've done weak acid and strong base, but now let's do it the other way around, strong acid and weak base. So for example, we'll go back to putting HCl in there, but we might add ammonia solution as an example of a weak base being added. So we're back to starting at pH 1, and in the low pH region up to around pH 7 it's not going to be buffering. It's only going to be buffering in the basic region because it's the base that's weak. So that means up to about pH 7 it's going to be very similar to the curve we had with HCl and a strong base. So we're going to get something that looks kind of like this. Okay, if this isn't the 25 cm cubed line. Okay, so it starts increasing gradually and then becomes much steeper and becomes near vertical when you reach the neutralization volume. But above that we're going to start getting buffering, and so it's going to stop being vertical pretty much around pH 7. And of course the limiting pH is not going to be as high as 13 because ammonia is a weak base. That means that the OH minus concentration is much less than 0.1 mole per dm cubed. You don't have to even know how to calculate the pH of weak bases, so this is purely going to be a matter of guessing that it's going to be less than 13, so make it somewhere maybe around 11 or something. So we can say, right, that's going to be our limiting pH. And again, just like we did with the weak acid, you just sort of get this buffering kind of effect. So oops, that's a bit messy, but don't worry too much about the shape. But the important thing is that it stops being vertical, more or less around pH 7. So again, that's very much identifiable as strong acid, weak base if you see a vertical region, but it's only below pH 7. So the final case we can think about is what happens if we have a weak acid and a weak base. Okay, so we're going to stick with ammonia as our base, because then we have a weak base going in, but this time we're going to have ethanoic acid as our acid. So both the base and the acid are weak. So let's come to the curve. Here's our pH 7 line, and here's our neutralization volume, because they're still equal concentration, so it's still going to be neutral at 25 cm cubed. But what's the curve going to look like? Well, it's a weak acid, so it's going to start up here somewhere, and it's going to buffer in this region, so no vertical region below pH 7, so we're going to get something that looks kind of like this. And then it's a weak base, so no vertical region above pH 7 either. So again, if it's going to finish somewhere maybe around 11, we're going to get a curve that looks sort of like this. So it's very different because there is no vertical region if both the acid and the base are weak. So that curve is very easy to identify in that sort of situation.